Welcome to my channel, Perry University. For this video, we're going to talk about some very basic terminology needed for just the very fundamental levels of computer logic systems, kind of intro courses. First, we're going to talk about abstraction, which is something that you use every day, whether you realize it or not. Next, we're going to talk about the three Y's of abstraction, kind of break them down. It's going to be hierarchy, modularity, regularity. Then we're going to talk about a few other little things that are going to be needed for future videos and future lectures. All right, so first, what is abstraction? So if you look, we have an engine block, crankshaft. These are going to be your cylinder heads, cylinder arms, have gaskets. These are all pieces of an engine. But when you're referring to your engine, you're probably not referring to all those individual pieces. You're not going to go to the mechanic and just list out every piece of your engine. You're just going to say your engine. That simplification is abstraction. So like I already have circled here, here's an alternator, serpentine belt. You see your spark plugs. Once again, this picture is the simplified version of the previous picture. It's all just stuff put together. You've abstracted all the unnecessary detail, and now you just have an engine or a motor, and that's what you refer to it as. Same thing can be said for like a car in general. You don't refer to your car as the engine, the axles, the tires, the seats, the steering wheel, steering column, transmission. You just refer to it as the car, even though all those things make up your car. That loss of the detail for a grander, more generalized picture is abstraction. So now let's define abstraction. Abstraction is a less detailed summary that represents something more complex. And anytime you're abstracting something or creating a more generalized picture from kind of lengthy, unnecessary details, you need to ask yourself two important questions. Number one, are the needed details there? Because you still need to convey the point. Number two, are unneeded details there? Because if you're abstracting, the goal is to make it as simplified as possible while still getting the point across correctly. So now we're going to talk about the three Y's of abstraction: hierarchy, modularity, and regularity. First, let's talk about hierarchy. Hierarchy is an arrangement of modules ordered into a rank. Low-ranked modules are specific. They belong to more general, high-ranked modules. So as you're down here, like I already have some stuff circled, logic gates, those are your building blocks. They're very specific. They can be combined to make a module, such as a half adder. You can put modules together, like multiple half adders can go together, and those multiple half adders combined will make a full adder, and full adder can become combined with other full adders to make something really big, or other functions, other modules. Next thing you know, you've got a calculator, which would be a system. So let's think of hierarchy from another standpoint, more biology, chemistry related. So you have electrons, protons, neutrons. They make up atoms. Atoms then make up molecules. Molecules make up large compounds such as lipids, carbohydrates, proteins, nucleic acids. Those combine to make cells, and then cells can make tissues. Tissues can make organs, and then a bunch of different organs will make organ systems, and then a bunch of different organ systems together makes up you. That is a hierarchy going all the way down from those fundamental electron, protons, neutrons, all the way up to a full-blown multicellular organism such as a human or any other kind of animal. Next, we have modularity. Modularity are the individual modules which have well-defined functions and interfaces. So this picture here, this is a half adder. So let me change color here. So this top part, this is a NOR gate, which we'll get into that later. And this bottom one here, this is called an AND gate. Again, we're going to talk about these later. Don't worry about it right now. But these two inputs, A and B, have an output, S for sum, C for carry, and this makes up a half adder. This half adder is a module. It is something that actually does something. This is something that can be used repeatedly, and it has a very well-defined function and an interface. You know exactly what it is, know exactly what it does. Next is regularity. This is kind of where the production line comes into play. repetitive design with rules for regularity. The same component can be placed in a variety of systems. So just like all these cars, this is the same. Oh, let me change to a different color. All right, let's try white. So all these cars have the exact same wheels and tires, right? So those are modules, but they are regular. There's a rule, they have set dimensions, set materials, and they can be placed on any one of those cars. You can take this wheel and tire and place it on this car all the way back here, no problem. That regularity is what allows things to be produced kind of on a mass scale. And remember, it's repetitive and has rules. The rules part is really important. All right, next, let's talk about just some general terms here. So like, what's a module? A module is a component, a unit, or a division of a large system. These three properties are pretty important, and for a logics class, they're probably going to want you to know these. Number one, it has a well-defined function, such as the half adder. That has a well-defined function of taking two inputs, creating a sum and a carry. It has a formal list of inputs and outputs. The half adder, again, has inputs A and B, and outputs S and C. And it has a name, such as a half adder. Its name is half adder. And there you go. And also important for a module is actually does something. It performs some kind of task. Let's talk about elements. Element is the active electrical component of any kind of circuit, whether that's resistors, logic gates as shown below, voltage sources, capacitors, inductors, whatever it might be. So down here, like we have an AND gate. These are both NOT gates. That's an OR gate, that's another AND gate, and that's another OR gate. Every one of those is an element. A, B, and C over here are not elements, they're inputs, and Q over here is an output. But remember, the elements are these gates. All right, now digital versus analog. Another pretty important concept, digital has a finite number of possibilities. At the level we're at, it's going to have two options. It's going to have either 0 or a 1. So off for 0, excuse the handwriting, and on for 1. And over time, something's going to be off, and then it's going to turn on. Then it's going to be turned off, then it'll be turned back on. Go, turned off. It's going to look just like that. You're either down here off, or you're up here on. That is basically what binary is, off or on. Analog, that comes from nature, and there's an infinite number of possibilities. Think about a sine wave. The number of values from here to here is infinity, right? Same thing from 0 down to -1. There's actually an infinite number of values. So these are like seismic graphs or something, anything like that. They're just all over the place. That's not what we're going to be dealing with at this level. You're either going to have off or you're going to have on. And that is digital and that is analog. All right, I'm going to leave it here. This is kind of a very important tip. From now on in logics and computer classes, you're going to be counting from 0. Everything starts at 0, 1, 2, 3, 4, 5, which is 6 numbers, but you're still going to start from 0, knowing there's 6 values there. That is something you're just going to have to get into, a habit that's going to have to form. It's going to pay dividends later on in our next video when we start talking about binary. Thank you for listening. I appreciate it very much. I hope you have a great day.